Alright, so I just want to show very quickly how you can add vacuum to structures for electronic structure calculations. So I'm kind of assuming you know what this means already if you're at this video, but basically the idea is if you're using a code, maybe a DFT calculation, something like that, which employs periodic boundary conditions that you can't turn off, things like quantum espresso, VASP, and these types of things. Those are really the two most common that come to mind. I think some others might have the same sort of like unremovable PVCs. But the idea is if you are for some reason using one of these codes to look at cluster models or something which is periodic in 2 dimensions or 1 dimension, then what you need to do is make sure along the aperiodic directions that you have sufficient space between the cells. So I'll just add a second cell here. Basically, if I want to model this as a cluster, I need to make sure that this and this, the first periodic image, are sufficiently far away from each other that we're not getting these kind of interactions. So basically that they're electronically decoupled from one another. That's a very important thing to do. You have to test how far they need to be separated for that to be the case, but that's what we're looking at here. And I'm going to show you how to do that for 0D, 1D, and 2D structures. So first thing you'll need is, well, I guess the very first thing you'll need is a Python environment. Then you'll need a ASE, atomic simulation environment. So you can, once you have a Python environment set up, you can do conda, assuming you have conda. If not, you can just pip install it. But conda, install channel conda forge ASE. That will give you ASE. I already have it, so I'm not going to do that. And then I'm just going to open a Python interactive shell. You can, of course, copy paste these exact same commands into a script and kind of loop through a number of materials if you like. And this is really the benefit of doing it this way over with a visualizer. One, this way is going to be very exact. You can specify exactly how much vacuum you want. If you're doing this with a visualizer like Vesta or Avogadro, you kind of have to, there's some guesswork in terms of manually changing cell parameters, and it's a bit annoying. So this is a very quick way to do it. We'll need a couple of functions. If say you're coming in with, presumably you have your own crystal structure that you're trying to deal with, or maybe not a crystal structure, but you have your own system that you're trying to deal with, you can import ase.io, and I'll show you how to do this with one of the 2D materials in a minute. But for now, we're just going to create them. So you import ase.build. This is a set of basically functions that allow you to create some crystal structures, whether it be a specific face of a crystal or a TMD. I'll show you how to make a TMD with it, or graphene nanoribbon, all sorts of things. And also just simple molecules. So let's set up a 0D, a 1D, and a 2D system. So for the 0D system, I'll just use a simple water molecule. So we'll do ase.build.molecule, and then it has H2O built in as something it can recognize. Then for a 1D system and a 2D system, we'll do the exact same thing. ase.build.mx2, this will give you a TMD, and we'll give it, let's make it like 4x4x1. That's the size here. So it's basically size of a supercell. And then for 2D, we're going to deal with the same system here, but we'll just do some different things to it to add the vacuum. So let's view the 2D system, the MX2, basically, the TMD. And you can see that we have a cell created for us, given by this dashed line, but of course it's only 2-dimensional. So it's not like a real cell that you could plug into a code which has 3D PVCs. And what we're looking at with the molecule, whoopsies, view 0D, what we're looking at here with the molecule is just there's no cell at all, of course. So the way that you would add vacuum to the 0D system, that could be a cluster model of something, it could be a simple molecule, or it could be a quantum dot, for example. What you do is you simply do 0D.center and then give it how much vacuum you want. Vacuum equals however much vacuum you desire. Now if we view this, we have a centered water molecule in a 20, well, actually not 20 by 20 by 20, but basically this distance from here to here will be 20. So create this. If we measure the distance between these water molecules, it should be about 40 angstroms, right? It won't be exactly 40 if you have something of a larger extent. For example, if we do it along the z dimension, and we look at, you know, it's hard to click here to here, you know, it's not going to be exactly 50, oops, but it will be pretty close, right? So the idea is that now you have your system set up and good to go. So what you do now is, if you're trying to copy paste these coordinates into a code like Quantum Espresso, or a code where you need the positions explicitly as well as the cell, you can just type in 0d.cell. Those are your cell parameters, and when they're given in this format, that basically means that your cell angles are 90, 90, 90. So it's a cubic cell, or an orthorhombic cell, at least. Now, that's kind of a standard thing you'll see. And you can get the positions either in Cartesian coordinates, so in angstroms, so 0d.get positions will give you that. But you can also do get scaled positions. These will give you the positions relative to the cell vectors. This is useful in a lot of cases, and some codes will kind of prefer this input over the other. So you have a way to get both of those. And if you're ever wondering which chemical symbol this particular atom applies to, you would just basically do 0d.get chemical symbols, and it will give you the order. So this is your oxygen, water, or rather hydrogen, hydrogen. So that's what you do with the 0D system. You can then write it to a CIF file if you like. That will keep the cell parameters for you, or you could do just an XYZ file. At the very end, I'll show you kind of some working with files, because presumably that's what people are here to do. But yeah, so now moving on to the 1D system, what we'll do is pretty much the same thing. So let's just view it real quick. So we have a 4x4x1 TMD, and now we're just going to try to remove periodicity along, say, the B direction and the C direction, but we'll keep it along that A direction. So the way that you do this is you do 1D.center, exact same thing that we're going to have done before, but we'll give vacuum equals, let's say 12 angstroms. And then we have to pick the axes that we're going to do the vacuum along. So if we want it to be periodic along the X and Y directions, or rather along like the second two directions, so Y and Z or B and C, then we just give the indices of those axes. So 0 corresponds to X or A, and so on. So we'll just do this, and now if we actually view the structure, you can see that we have removed periodicity along this B direction as well as this C direction, but it remains along this A direction. And you can kind of check that this is the case. Just hit R, and you can see that we basically have a nanoribbon at this point. And these periodic replicas are, you know, sufficiently far apart, presumably, for what we're looking into here. And that would be your setup. So you can, again, write that to a CIF file, write that to an XYZ file, and keep the cell parameters on record for when you need to set up your input file. Now for doing a 2D system, it's actually the exact same thing. So we'll just do 2D.center, vacuum equals, say, 20 angstroms, and we'll have just that vacuum along the Z or C direction. Oops. Axis equals 2. Now if we do view 2D, then you see that we've done the same thing here. So you can kind of repeat along here, and you see that you have this correct setup. So you can now write this to a file. I'll show you a few different types of files. So you just do 2D.write, 2D, well, let's write as MOS2 dot sif. You can also do a Vesta or a VASP. I don't know if you can do a Vesta. Let's actually test it. Okay, so you can't do it to a Vesta, but you can do it for a VASP, and you can also do it for an XYZ. Now, I'm going to print out the cell here. So let's do 2D dot. We have this. These are the cell parameters, basically giving you the coordinates for the 3 lattice vectors. And this is what you need to have if you're saving these types of things to an XYZ, or if you're going to manually input the cell parameters into your DFT calculation, like you have to with Quantum Espresso, for example. So I'm just going to save that to a variable, 2D.cell equals, or rather cell temp equals, and then I'm going to show you how to reload the structure. So if we were to have just the Cartesian coordinates of this, we can read these in now, say new 2D equals ASE.io.read. So this is what you're going to do if you have your own structure as an XYZ or a CIF. If you have it as a CIF, then the cell stuff is already included, obviously, in a CIF file. So you don't need to do this extra work. You just read it in. But if you only have your coordinates as an XYZ, then you need to re-add those cell parameters. Or you need to be ready to put them into your Quantum Espresso input or your VASP input, whatever. So we have this now, and if we view MOS2, it's going to be the exact same, view, rather, new 2D. We have the information, and because actually ASE does write XYZs with cell information. Look, so I'll show you that real quick. If we open MOS2.xyz, then it actually keeps the lattice information here, but a standard XYZ file is not going to have that. It'll have your number of atoms, it'll have some description for the system, but usually not the lattice. And then it will have your atomic positions. So that's what we're looking at here. If you don't have that, then all you do is Python. We have to re-import some stuff. Import ASE.io. I'm going to actually delete that so that I can show you. So if we, we have a bunch of examples. So we'll delete this and just write MOS2. So that just, now when I import it, it's not going to give you the cell information. So import ASE.io. We're just going to read it in like this, and it was MOS2.xyz. Oops. There we go. Now we'll import the view function again. So from ASE.visualize, import view A. And now you'll see we have our positions, but we don't actually have the correct cell parameters. So what I'm going to do is grab these coordinates, copy them, and then I'm going to effectively just reset that. So A.cell equals this. Now if we view A again, it will have the proper cell parameters. And so that will be good for you. And that's exactly how you do this with a 0D structure, 2D structure, 1D structure. A little bit longer of a video than it really needs to be, but I hope that is helpful for you, and I hope you can actually see the benefit of doing it this way over manually with a visualizer. Because one, you're getting to set that vacuum exactly in a precise way, not by hand. And two, everything's centered nicely in your cell because we're doing this with the center function. And three, it's, like I said, very easy to sort of loop through a bunch of structures and do this. So, if all you needed was, that information, then that's great. But now I'm going to show people who may want to set this up for a large number of structures, prepare a large number of 2D materials for electronic structure calculations. I'm going to show you how you would do that. So we're going to use a Python script for this. Let's call it, I don't know what I put in this vac, ex.py. Yeah, this is fine. So now this is just kind of like a little fun side project you could do that will kind of loop through a bunch of, for example, TMDs and create those and prepare those all in a way that you're ready to do some electronic structure calculations on them. So this would be more fitting for a sort of high throughput type of setting. Of course, you need a thing to build these structures. This exists for TMDs, but maybe you want to do it for some other class of materials, like MXenes or whatever those things are called, quantum dots, or, perovskites. So you'll need a tool to build those if you're not doing it with something that ASE has a build tool for. But I'll show you regardless. So let's say, for example, we want to prepare a whole class of TMDs. Then let's say mlist equals, we're going to give a list of basically the m and the x components. So we'll say mlist equals, we'll do w, mo, and we'll just do these for now. Oops. And then we'll do xlist, and we'll have te, let's have s, let's have, well, we'll just do these. I mean, a few will serve the purpose of kind of showing you what we're working with here. Then what we'll do is loop through both of these lists. So for I, well, I'll call it for m in mlist, and then for x in xlist. Then we can do the same thing here. I'm going to move this to a folder to kind of hold all of our new files. We'll just call it TMDs, cd TMDs, copy that Python script, and then we'll go through this. So what you would do is basically do what we did for that one system, but for all of these. Maybe you want to define a dictionary that will give you a good prediction of what the kind of baud lengths should be between the m and x here, but it's up to you. You could also loop through the different phases, H and T phase, things like that. But what we're going to do now is call it like this TMD equals ase.build.mx2. And then what we're going to do is we'll just say m plus x plus 2. That will give us our string. That will be what we're trying to create the TMD for. And then pick your supercell size. So we'll just do 4 by 4 by 1, for example. And then we just need to add the vacuum. So this TMD.center vacuum, say 12 angstroms is a good amount of vacuum, and then axis would be 2. Oops. And then we're actually good there. Now what we would do is we would want to write this to a file, presumably, so that we can feed these into our DFT calculation as an example. And then we'll just name it, basically the same thing here. And then add a file extension, so we'll just save them as CIF files. And then we will be done. That's really it. So delete these, Python back. It's going to create those files, and now we have MOS2, MOTE2, WS2, WTE2. And then if you want to view some of these, you can use ASE GUI from the command line, WTE2, for example, and then we can see that we have nice tungsten ditelbrad. And we can do the same thing with all of them if you really wanted, but of course, we know that they're working properly. And then you could set up your DFT calculator using ASE, for example, to read in these things as CIF files, create an atoms object out of them, and then a loop through to your DFT calculations. So that will wrap it up. 20 minutes, first roughly 10 minutes, showing you how to add vacuum in a quick way, and then giving just kind of a fun extra here for how you might set up some high throughput calculations using ASE. So I hope this video is helpful for you. If it is helpful for you, leave a like down below. If you have any questions or anything like that, you want me to show something else, or you want me to sort of show you how you might do those high throughput DFT calculations also, then also just leave a comment, question, anything like that. And I appreciate you watching, and I hope this was helpful.